Yeah.
This is my engineering stress income. You can see that's limit of proportionally elastic, yield point, ultimate, and then picture, right? This is your engineering stress strain typical diagram. So if you see here, it is you are having, let's say, 310, that's a 450, but you can see that's a negative. When you draw this, it will come between 310 and 450. But what is the universal testing machine says? What is the testing says? Metal testing. You will keep on increasing until the product fell into pieces, right? So that means you should not get like this, it should go up like this, correct? After ultimate also. You getting it?
Yeah.
But it is not there in your engineering book. It is like this. So your now that your limit of proportionality become A to A1 in true stress, B to B1, C to C1, a D to D1. Now this is the actual curve, your actual testing curve, okay? Because as you keep on increasing the load up to limit of it will go like this, you increase up to ultimate, then and then finally break. So it will break only when you keep on increasing the load. So when you keep on increasing the load, of course the stress will also increase. It's not like this here it going down, stress decreasing. Getting it? So let's say ultimate is 450, but in fracture you draw the line here, it will come around 310. So this is wrong. Fracture always, the final product fail at the stress that is always greater than to the ultimate in reality, right?
So that is because the cross sections are changing, right?
Yeah, see, in this curve, what happening is we are not accounting what changes happening during this process. We are keeping what here, same will be here. Correct?
Yeah.
But here it is not the case. We are keeping all stuff changing as as we are changing the loads. Okay. So this is your conventional engineering stress strain curve. This is your true stress strain curve. Okay. So D will be your breaking point, or you can say it's going to be your fracture point. That's also your breaking or fracture point. So they will ask you to draw this curve, and make sure you will show the after ultimate goes up like positive. Make sure you show this negative. Stress value less than ultimate in the engineering. So breaking point, D point, breaking point value is less than into the ultimate tensile stress. BP is less than to the ultimate tensile stress in engineering stress strain curve, right? The nagging will start here, stress value at maximum load. You can see this is your ultimate stress 450, but breaking stress you are getting 310. That's why the breaking point stress is less than to the ultimate in the engineering stress strain curve, right? So in true stress strain curve, the breaking point or a fracture point stress value is always greater than to the ultimate tensile stress, because we are considering instantaneous cross section area and the instantaneous length in our calculation. Clear this thing?
Yes.
So this is the very important graph. You have to basically, you should be like, remember all the time. Okay. So it become very easy, clear crystal, right? Crystal clear, correct? As you keep on increasing the load, of course, practically it should go up, right?
Yeah.
So true stress is equals to engineering stress into exponential of 2 strain. So first we need 2 strain, correct? In order to get 2 stress, sigma t. So we need a ET. So true strain equals to ln analog of 1 plus E. So here just type equal to, type ln, okay, clicked here, ln 1 plus, what is this, 1 plus E. E is mean your engineering strength, that's one. Then just close the bracket, enter it. Make sure you should also get here 0 value, okay. Then just simply drag and drop. It is not taking, I don't know why. See this, okay. So that's your true strain value. So your engineering strength, that's your true strain. You can see it is always differing, changing. Okay. Now here in true stress, what is the formula? Engineering stress into exponential of true strain. So equal to engineering stress, this one, multiply exponential E x p, right? Just this one, exponential of true strain. Close it, enter, right? Okay, then just simply double click. See this. You can see now graph. Can you see this?
Yeah.
So this is going little up. So actually, let me tell you one more. Yeah, this you understood?
Yes, right. So those are the strength and strain curves, right? Red and blue.
This is your true stress strain curve. This is your engineering stress strain curve, blue one,
Oh, अच्छा, okay.
right? See this. That's your engineering stress strain. This is your true stress strain. Can you see this? Right. So we are having up to 0.9 means 1 mm here. Here it is 1600. So it is going up to 1330 here, right?
Yeah.
Stress. Can you see? Have you seen this one more important thing, that this up to this curve, limit of proportionality. This is completely like overlapping, correct?
Yeah.
So basically, this A point, actually we have exaggerated, but it should be like,
Yeah, closer to the magenta line. Correct. Okay.
it will be like this, correct?
Yeah, true.
Up to here now, because nothing will change up to here. Then you can, now it get changed, correct?
Right.
It should be like this. So up to here, it almost, limit of proportionality up to here, it is almost same. Okay, and then now it get changed. Yeah, see this, exactly same up to the yield point. Can you see this?
Yes.
So up to the yield, it should be very close. Then now it shows go up. Okay, not like this. So up to the yield, we should have exactly almost same. Correct?
Yeah.
If you look at the mechanism of plasticity, like plastic deformation in the metal is due to shear, but in the rock and soil because of the pressure. But we will going to discuss about metal point of view. So what happen whenever you have any raw material? So there are a lot of atoms. So sliding of these atoms planes over the one another at a molecular level will cause the plastic deformation at continuous scale. So if you see here, now you have to keep in mind that we are discussing after the yield. Okay, so let me tell you here, now we are discussing like how loading and unloading happens in the ductile material. So let's say this is my stress strain curve, that's my yield, that's my initial yield. Okay, this is going to be your elastic, this is going to be your elastoplastic. Now what is this elastoplastic? I will explain in a minute. So when you load the ductile material within the range of elastic before the yield, when you unload it, it will follow the same path, right? It will regain its original shape. But when you go to the elastoplastic region, it will follow the imaginary line, or the follows this line. So the unloading happens in elastic region. The loading unloading follows same path, But in elastoplastic region, the loading unloadings are different. Unloading follows the elastic, unloading path is basically elastic and parallel to this point or parallel to this line. So this is how basically loading and unloading happens. Loading unloading means you're loading the product and then you're removing the product, right? So within the elastic zone, this will follow like this. It follows the same line. But after the beyond the elastic zone, like elastoplastic region, it will follows this parallel line and just go like this. Then you further wanted to load, then it will go start from here. That is called reloading. Okay. Okay, so that's going to be your yield point, and then so this going to be your that's your yield. Stress, strength, that's your sigma y yield. Okay, let's say I started with 0, 0.
Okay.
Now this is your linear curve, or your, we call it as a Young modulus, right? Okay, this we call as a bilinear curve, or we call as a elastoplastic. Both are same. This we call as a tangent modulus, you can say. Modulus, or in answers we call this as a bilinear. Okay, so in elastoplastic, also we call as a elastoplastic. Okay, also we call this as elastoplastic. Now what is elastoplastic means? If you see here, that's your elastic part, elastic strain, right? Now that side is here going to be your plastic strain, correct? Okay.
Yeah. Yeah.
So if you can see here, there will be a one angle here. Okay, this is we call as a tangent modulus curve or bilinear curve. So basically in elastoplastic, what will happen, as you keep on increasing, for example, let's say I having 0.2 strain here, and let me go to this point, and let's see here this point. Okay, so if you go down, okay, here, here, okay, so let's say it is 0.4 here, let's say 0.6, 0.8. So what happening here, as you keep on increasing the stress, see, stress is also increasing, right?
Yeah.
Right, so let's say you are having here, for example, 300, okay, let's say your yield is 300. Okay, then you are having, let's say, 310, 350, let's say 400, right? So as you keep on increasing the stress, what happening, the strain is also increasing, correct? This is comes under the bilinear curve. So bilinear curve, what happening here in the bilinear curve? In the elastoplastic curve, stress and strain both increase, correct?
Yeah.
Okay, so that's happened in the elastoplastic curve. This is got clear.
Yes.
Now coming back to loading and unloading. Now coming back to these 2 points also. In the ANSYS, in the bilinear curve, you need, so what you need here basically, what data you need stress versus stress data, right? Correct?
Yeah. Yeah.
So you need stress versus strain data, okay? Coming back to okay, now in the bilinear curve in ANSYS also you can define this called tangent modulus. So what you need here is you need okay, so you need this value. Okay, in case of when you go for bilinear, in case of ANSYS, okay?
Okay.
Here. Okay, so now coming to the loading unloading, what happens?
Yeah, unloading in the elastic region, it will go back to the original state.
Yes. So unloading will going to have the it should be parallel to this line. Which line? This line, correct?
Yeah.
So here what happening, loading within this range, if you load the product, then unloading also happens in the same direction, correct? But when you further load the product, so here what happened, unloading follows the parallel to this line, clear, parallel to your Young modulus line. This is clear, loading and unloading.
Yes, sir. To reiterate what you said, within the plastic region, in your example, if you apply 3 times loading, also if we unload 3 point in time, it will go back to zero as strain. And beyond 300, for example, if you are applying 400 and if you are unloading 400, then it will come back to almost 0.5 per strain, change in shape. That is what I am understanding.
This is clear, right? Correct?
Yeah.
So this is one curve. Now coming back to another, we have one more in the velocity called so what happens here? So see here, that's your sigma y. Okay, now let's take some points. Okay.
Okay.
So here, so what we have in this perfect plastic curve, right? The stress will be constant,
Yeah.
but strain varies, right?
Right.
Please. So this is what happens in the elasto, this is what happens in the perfectly plastic curve.
Plastic.
Okay, let's say you're having here 0.2, 0.4, 0.6, 0.8, 1, then 1.2, right? So what happening? The stress is constant, let's say 300, but strain is varying in this direction. This is called completely perfectly plastic material. So what you needed here, you need only one thing, strain data. Data, okay?
Okay.
Coming back to third one, so what happened here, that's called multilinear hardening material. So you got one stress here, then you further got it, then you further, then you further, then you further. Okay, sorry. Like this, okay, so this is we called multilinear hardening material.
Okay. Okay, you can see here. So in this case, what happening here is stress and strain both. So this is we call so here right? Okay.
Coming back to you understood, right? Correct this thing. Let's say sigma y, then
Yeah.
sigma 1, sigma 2, sigma 3, sigma 4, sigma 1, right? E1,
Yeah.
E2, 3, 4, 5, 6, and then E7, E8, so on, right? So this is what you need in the multilinear hardening. So these are the curve basically you need to used. So this is between the between your this is very highly used elastoplastic, especially for metals. So we can say it is like we are discussing before ultimate, between ultimate and the your yield.
Elastic.
Yeah, yield and ultimate, between that we are discussing. Okay, so
Okay.
this is basically in the metal these things happen usually. So this effect we call strain hardening effects. We can even study those things, but let me just go come back to the PPT also. I hope you understood this stuff, right?
Yeah.
We have to, now you understood, like we have to think about, in the plasticity one is three curve we understood, and the loading and unloading patterns are different in the elastic and the elastoplastic region. This is what is the outcome. Did you understood?
Yes.
So now when we talk about plasticity or elastoplastic, perfectly plastic, strain playing an important role, correct?
Yeah.
So we have to little dig more about strain, which is very important part here. So let's go here. Let's say this is elastoplastic again. You have loaded your part from 0 to yield. That's your initial yield. Then you are loaded, then further loaded from Y to A, and then you are unloading it. Okay, so unloading follows this line, right, parallel to your elastic lines or your limit of proportionality, you can say. So after you unloading, this much strain will be left. Okay, and this is going to be your recover plastic strain basically, right? Going into the, this is elastoplastic. Okay, now we have to go that. So that's your going to be your elastic strain, that's your going to be a plastic strain. So this equation, while you sum up, total strain is equals to elastic plus plastic strain, right? So this is going to be elastic strain, and in other words it's called recover plastic strain, because you are unloading it, right, to the product. So you loaded up to your loaded and then further unloaded. So this equation also called as additive decomposition strain, only applicable for small deformation. So we understood what is elastic strain and what is elastic strain in the curve. Now we have to understand that what this elastic strain do and what this plastic strain basically do separately in our material. So I have written one statement over here. Stress is related to elastic strain. I'm repeating these words again. STRESS, stress, is related to elastic strain. See this. So let's, now again we have loaded, right, again yield, then up to Y, then further loaded, and then unloading. So this time we are just putting some more points, let's say B and C and A, just putting some points over here. Same path, considering the point like A, B, C are unloading point. So what we can see from this curve, so A and B and C have the same plastic strain but different elastic strain, right? So when you plot this side, a different elastic strain. If you go here also, this side also, the stress will be different, right? All these 3 points. So stress are not related to the plastic strain. Stress are not related to the plastic strain. Plastic strain do not induce any stress. Basically, stress are depending on the elastic strain part of your curve. Stress are directly depending on the elastic part of your curve, not the plastic. This is what clear?
Yes, correct.
So now question arises, then what does the plastic strain contribute? Even before going to this question, in the next project we can see practically how stress is relating with elastic strain in our next project also. I think maybe we have one diagram, I think maybe like we can see in the next slide maybe. So now question arises, we understood the role of elastic strain in the SN curve, in the stress strain curve. Now, what about the plastic strain? We are saying the plastic strain do not induce any stress. Then what does this plastic strain contribute to? This is the plot which we are going to, do the simulation in the next project. Now you can see, now you can see in the exhaust manifold, this is the elastic strain plot, and that's your equivalent stress plot. This both plot, this both stress and the strain on this manifold we have plotted in the graph. Now you will observe that both graphs are completely matching each other. See this, all these points similarly, right? So even though you can look at the locations, see this location, see this and this. So whatever stress location, von my stress I'm talking, whatever von my stress location you will see in your product, right? If you are using cyclic loading pattern, because this is cyclic and highly, multi-linear hardening material. So whatever location you are getting in the stress, see at the same location you are going to having the strain also. Okay, you can see this both comparison. So that basically clear that the elastic strain is directly relating with the stresses. Now question comes in the brain is, then what is the contribution of plastic strain? Then what plastic strain then contribute, right?
Yeah.
So let's see here. We are writing the statement called strength, S-T-R-E-N-G-H-T. Strength is related to plastic strain. Strength is strength, not stress. It is strength. Okay, let's see how. You loaded your product up to P. P is your initial yield. Then you further loaded up to Q, and then you are unloading it from Q to R. Okay.
Yeah.
So this is completed my one cycle. Okay. Now this is my initial yield. Now after this completing one cycle, I want to reload this product from this point. So you further reload it. What will happen in the reloading? This initial yield, what you were like having earlier, this will going to shift. So this P become P dash. So during the reloading material, may you get yielding at the point P dash. That means strength, that means the material have gained some strength in corresponding to point P. So you can see, then you reload it. I'm just taking exaggerated line over here. So this P become P dash, and that's supposed to become here theoretically, but we got some more, right? The product got strength here, right, in the reloading. Now it is completely making cycle. So which could be your plastic strain, EP. So when material get strength, when the material get strength is known as strain hardening. When the material lose strength is known as strain softening. Okay. So what happening here in the next cycle, we are observed that material got some strength towards your yield point. That's why we calling this phenomena as a strain hardening. Getting it?
Okay.
But now actually it's not it is not that much understandable. Why? Because for example, take example of in general example, let's say you are having one material, okay, you are loading that material and then you further loading it and then you reloading it, but again you loading it. So what happening when you talk about loading means, or reloading means, kind of you are increasing the load, right? So as you keep on increasing the load, the strength of the material should get decreased. But here we are saying we got new yield point which is higher than to the old yield point. It means the strength will increase. So do you think that statement is right, or something is wrong in this statement?
Yeah, I feel something is wrong in the statement, sir.
Right. So ideally it should decrease, right? Not to the increase. Correct?
Yeah.
But here is one trick over here in the material, inside the material science. Let's see that.